Okay, so in this problem, we have a skydiver that's jumping from an aircraft. It's slow moving, and the diver has a terminal speed of 50 meters per second. And so our goal is to get the acceleration when her speed is 30 meters per second, the drag force, and the drag force when her speed is 50 meters per second and 30 meters per second. So let's write down the givens and we can discuss how to do the problem. M is 80 kilograms. And the V terminal is 50 meters per second. So I'll call that VT equals 50 and we want to know her acceleration when her speed is 30 meters per second. A equals question mark if V equals 30.0 meters per second. Okay, so let's go to a free body diagram for the diver and see what we can learn from that. So we have the weight down, and let's think about the moment that she's at her terminal speed. So the weight is down and the drag force is up, and then they balance each other out. I'm going to pause and review what the formula is for the drag force in relation to the velocity. So I reviewed the chapter and, it seems like we're missing a lot of information, like the area, the cross-sectional area, and the drag coefficient. But hopefully we can get through the problem without that information. So I'm just going to record the formula that the terminal velocity is equal to the square root of 2mg divided by d rho a. D is the drag coefficient, rho is the density of air, and a is the cross-sectional area. This is equation 6.9. So let's see. So this is what's going on for velocity of 50 meters per second. But if the velocity is 30 meters per second, so actually let me just label this VT. But if the velocity is 30 meters per second, then the drag force, the person is still going to be accelerating down. And so the weight force is going to be larger than the drag force. And we know that weight minus drag then is equal to ma, where I just chose down as positive, so we could end up with a positive acceleration. And then our goal is really to find this acceleration. And so we know that this acceleration is going to be the weight minus d, so that's mg, minus the drag force. And then we want to divide that by the mass. So it's going to be g minus d over m. And now we want to use the formula for the drag force. So, oh shoot, that's r. So I'm gonna use a notation consistent with your book and call this r, just to be as clear as possible. And I'll go ahead and write down the formula for r. I think I have it memorized. I think it's 1/2 d rho av squared. Let's double check if that's right. 1/2 d rho av squared. Okay, great. And so we can say that r is equal to this. So let's sub this in. So it's 1/m. Now let's sub in r, 1/2 d rho a v squared. So obviously we don't have a lot of this information, but hopefully we can use this information to help us out. So if we know the terminal velocity, what we can do is we can solve for d rho a, right? So we can get vt squared is equal to 2mg divided by d rho a, and then cross multiplying, we get that d rho a is equal to 2mg divided by vt squared. So now what we can do is sub in for d rho a. So then we get a equals g minus 1 over m times 1/2 times d rho a is 2mg over vt squared. And then that was, we subbed in for this. So that was this. And now we want to multiply by the actual velocity squared. So in this question, v is equal, or in this part, v is equal to 30 meters per second. Probably was other ways to think about this. This is the way that came most intuitively to me. So we get the m and the 2's cancel. And so we end up with the final formula that a is equal to g, and then factor out a g, 1 minus v squared over v terminal squared. And so actually this is really not bad. And then so now I can just sub this into a calculator. I was thinking of doing it in my head, but getting a little tired. 9.81 times 1 minus 30 squared over 50 squared. So that gives me, right, and the two speeds were 30 and 50. So that gives me 6.28 meters per second squared. And then we want, so now we're basically done because we can calculate everything pretty straightforwardly. So we want the drag force when the speed is 50 meters per second. So for when she's reached her terminal speed, then the drag force is just the weight. So that's just mg. So all we need to do is, oh shoot, I'm used to calling this d, but this is actually r in this book. So so it's just going to be 80 times 9.81. So with that, I get 785 newtons. And for C, we get, and we want it when it's 30 meters per second. And so we know that R is equal to this thing. So 1/2, I'll just rewrite it here, d rho a v squared. And we know d rho a is v terminal, or 2mg over v terminal squared. So I'm just going to sub in for this. So 1/2 times 2mg over vt squared times v squared. Those cancel. And we get something with the units of force, which is good. So it says 80 times 9.81 times 30 squared over 50 squared. So with that, I get 283 newtons. And then both of them are acting upward.